Hi, good day everyone. I am here to discuss Chapter 4.3 of Project Management, which is the Improving Cost Estimates. This section deals with a number of ways for improving the process of cost estimating and an easy way of measuring its accuracy. These improvements are not restricted to cost estimates, but can be applied to almost all of the areas in project management that call for estimating or forecasting any aspect of a project that is measured numerically. Given, for example, task durations, the time for which specialized personnel will be required, or the losses associated with specific types of risk should they occur. These improvements range from better formalization of the estimating or forecasting process, using forms and other simple procedures to straightforward quantitative techniques involving learning curves and tracking signals. Forms. The use of simple forms can be of considerable help to the project management in obtaining accurate estimates, not only of direct costs, but also when the resource is needed, how many are needed, who should be contacted, and if it will be available when needed. The information can be collected for each task on an individual form, and then aggregated for the project as a whole. Learning curves. So here's a given situational example. Suppose a firm wins a contract to supply 25 units of a complex electronic device to a customer. Although the firm is competent to produce this device, it has never produced one as complex as this. Based on the firm's experience, it estimates that if it were to build many such devices, it would take about 4 hours of direct labor per unit produced. With this estimate and the wage and benefit rates the firm is paying, the project management can derive an estimate of the direct labor cost to complete the contract. Unfortunately, the estimate will be in considerable error because the project management is underestimating the labor costs to produce the initial units that will take much longer than 4 hours each. Likewise, if the firm built a prototype of the device and recorded the direct labor hours, which may run as high as 10 hours for this device, this estimate applied to the contract of 25 units would give a result that is much too high. In both cases, the reason for the error is the learning exhibited by humans when they repeat a task. In general, it has been found that unit performance improves by a fixed percent each time the total production quantity doubles. More specifically, each time the output doubles, the worker hours per unit decrease by a fixed percentage of their previous value. This percentage is called the learning rate, and typical values run between 70 and 95%. The higher values are for more mechanical tasks, while the lower, faster learning values are for more mental tasks such as solving problems. A common rate in manufacturing is 80%. For example, if the device described in the earlier example required 10 hours to produce the first unit, and this firm generally followed a typical 80% learning curve, then the second unit would require 8 hours, the fourth unit would require 6.4 hours, and the eighth unit 5.12, and so on. Of course, after a certain number of repetitions, say 100 or 200, the time per unit levels out and little further improvement occurs. Mathematically, this relationship we just described follows a negative exponential function. Using this function, the time required to produce the nth unit can be calculated as this formula, where Tn is the time required to complete the nth unit, T1 is the time required to complete the first unit, and R is the exponent of the learning curve and is calculated as. Tables are widely available for calculating the completion time of the unit n and the cumulative time to produce units 1 through n for various learning rates. The use of learning curves in project management has increased greatly in recent years. For instance, methods have been developed to approximate composite learning curves for entire projects, for approximating total costs from the unit learning curve, and for including learning curve effects in critical resource diagramming. The conclusion is that the effects of learning, even in one-time projects, should not be ignored. If costs are underestimated, the result will be an unprofitable project and senior management will be unhappy. If costs are overestimated, the bid will be lost to a safer firm and senior management will still be unhappy. Tracking signals. PMs and others involved with projects spend much time estimating activity costs and durations, among many other things. There are two types of error in those estimates. First, there is random error. Errors are random when there is a roughly equal chance that estimates are above or below the true value of a variable, and the average size of the error is approximately equal for over and under estimates. If either of the above is not true for an estimator, Either the chance of over or underestimates are not about equal, or the size of over or underestimates are not approximately equal, the estimates are said to be biased. Random errors cancel out, which means that if we add them up, the sum will approach zero. Errors caused by bias do not cancel out. They are systematic errors. Calculation of a number called the tracking signals can reveal if there is a systematic bias in the cost and other estimates, and whether the bias is positive or negative. Knowing this can then be quite helpful to a PM in making future estimates or on the critically important task of judging the quality of estimates made by others. Consider the spreadsheet data in this figure, where estimated and actual values for some factor are listed in the order they were made, indicated for ease of reference by period. In order to compare estimates of different resources measured in units and of different magnitudes, we will derive a tracking signal based on the ratio of actual to estimated values rather than the usual difference between the two. To calculate the first period ratio in this figure, for example, we would take the ratio 163 divided by 155, which equals to 1.052. This means that the actual was 5.2% higher than the estimate, a forecast that was low. In column D, we list these errors for each of the periods and then cumulate them at the bottom of the spreadsheet. Note that in columns D and E, we subtract 1 from the ratio. This centers the data around 0 rather than 1.0, which makes some ratios positive, indicating an actual greater than the forecast, and other ratios negative, indicating an actual less than the forecast. If the cumulative percent error at the bottom of the spreadsheet is positive, which it is in this case, it means that the actuals are usually greater than the estimates. The forecaster underestimates if the ratio is positive and overestimates if it is negative. The larger percent error, the greater the forecast bias, systematic under or overestimation. Column E simply shows the absolute value of column D. Column F is the mean absolute ratio, abbreviated MAR, which is the running average of the values in column E up to that period. The tracking signal listed in column G is the ratio of the running sum of the values in column D divided by the MAR for that period. If the estimates are unbiased, the running sums of ratios in column D will be about 0, and dividing this by the MAR will give a very small tracking signal, possibly 0. On the other hand, if there is considerable bias in the estimates, either positive or negative, the running sum of the ratios in column D will grow quite large. Then, when divided by the mean absolute ratio, this will show whether the tracking signal is greater than 1 or less than 1, and therefore greater than the variability in the estimates or not. If the bias is large, resulting in large positive or negative ratios, the resulting tracking signal will be correspondingly positive or negative. It should be noted that it is not simply the bias that is of interest to the PM, although bias is very important. The MAR is also important because this indicates the variability of the estimates compared with the resulting actual values. With experience, the MAR should decrease over time, though it will not reach 0. We strive to find a forecasting technique that minimizes both the bias and the MAR. By observing her own errors, the PM can learn to make unbiased estimates. When meeting with their subordinates in order to coach them on improving their estimates, it is important to recognize that most overestimates of duration or resource requirements are the result of an attempt by the subordinate to make safe estimates, and underestimates result from over-optimism. If subordinates overcorrect, the PM should avoid sharp criticism. Reasonable accuracy is the goal, but the uncertainty surrounding all projects does not allow random estimate errors to vanish. Other factors. Studies consistently show that between 60 and 85% of projects fail to meet their time, cost, and/or performance objectives. The record for information system projects is particularly poor, it seems. For example, there are at least 45 estimating models available for IS projects, but few IS managers use any of them. While the variety of problems that can plug project cost estimates seems to be unlimited, there are some that occur with high frequency. Changes in resource prices, for example, are a common problem. The most common managerial approach to this problem is to increase all cost estimates by some fixed percentage. A better approach, however, is to identify each input that has a significant impact on the cost and to estimate the rate of price change for each one. The Bureau of Labor Statistics in the U.S. Department of Commerce publishes price data and inflators or deflators for a wide range of commodities, machinery, equipment, and personal specialties. Another problem is overlooking the need to factor into the estimated costs an adequate allowance for waste and spoilage. Again, the best approach is to determine the individual rates of waste and spoilage for each task rather than to use some fixed percentage. A similar problem is not adding an allowance for increased personnel costs due to loss and replacement of skilled project team members. Not only will new members go through a learning period, which increases the time and cost of the relevant tasks, but professional salaries usually increase faster than the general average. Thus, it may cost substantially more to replace a team member with a newcomer who has about the same level of experience. Then there is also the Brooks mythical man-month effect, which was discovered in the IS field but applies just as well in projects. As workers are hired either for additional capacity or to replace those who leave, they require training in the project environment before they become productive. The training is, of course, informal on-the-job training conducted by their co-workers who must take time for their own project tasks, thus resulting in ever more reduced capacity as more workers are hired. And there is the behavioral possibility that, in the excitement to get a project approved or to win a bid, or perhaps even due to pressure from upper management, the project cost estimator gives a more optimistic picture than reality warrants. Inevitably, the estimate understates the cost. There is a clear violation of the PMI's code of ethics. It is also stupid. When the project is finally executed, the actual cost results in a project that misses its profit goals or worse, fails to make a profit at all. Hardly a welcome entry on the estimator's resume. Even organizational climate factors influence cost estimates. If the penalty for overestimating costs is much more severe than underestimating, almost all costs will be underestimated and vice versa. A major manufacturer of airplane landing gear parts wondered why the firm was no longer successful over several years in winning competitive bids. An investigation was conducted and revealed that, 3 years earlier, the firm was late on a major delivery to an important customer and paid a huge penalty as well as being threatened to lose a future business. The reason the firm was late was because an insufficient number of expensive, hard-to-obtain parts was purchased for the project and more could not be obtained without a long delay. The purchasing manager was demoted and replaced by his assistant. The assistant's solution to this problem was to include a 10% allowance for additional hard-to-obtain parts in every cost proposal. This resulted in every proposal from the firm being significantly higher than their competitors' proposals in this narrow margin business. There is also a probabilistic element in most projects. For example, projects such as writing software require that every element work 100% correctly for the final product to perform to specifications. In programming software, if there are 1,000 lines of code and each line has a 0.999 probability of being accurate, the likelihood of the final program working is only about 37%. Finally, a serious source of inaccurate estimates of time and cost is the all too common practice of some managers arbitrarily to cut carefully prepared time and cost estimates. Managers rationalize their actions by such statements as, "I know they have built a lot of slop in those estimates," or "I want to give them a more challenging target to shoot at." This is not effective management. It is not even good common sense. Cost and time estimates should be made by the people who design the work and are responsible for doing it. As we argued earlier in this chapter, the PM and the team members may negotiate different estimates of resources, needs, and task durations, but managerially dictated arbitrary cuts in budgets and schedules almost had lead to projects that are late and over budget. There are numerous ways to improve the process of cost estimation, ranging from simple but useful forms and procedures to special techniques such as learning curves and tracking signals. Most estimates are in error, however, because of simpler reasons such as not using available tools, common sense, or failing to allow for problems and contingencies, such as having to replace workers midstream. In addition, there are behavioral and organizational reasons, such as informal incentive systems that reward inaccurate estimates.